A third linear model that we're going to concentrate on today for the in-class session as well is the logistic regression model. We've seen that all three models use the signal of theta times x in different ways. Again, just to recap, in linear classification, we use the signal by thresholding it against a zero sign. This creates a dichotomy between the positive and negative class and can be generalized to multi-class classification. You can think about how. Secondly, we can do linear regression, which takes the signal and uses it directly as is. Finally, we have logistic regression, which takes the signal and compands it between an upper bound of +1 and 0. This allows a probabilistic interpretation of the outcome. So in order to achieve the companding of the signal to be between 1 and 0, which allows us to make a probabilistic interpretation, we need to choose a specific function to put the signal through. We can choose any form for our function g, but we might want to choose one for our convenience. We would need one in this type of form, where when the signal is very large, we would say that it has a high likelihood of being a positive event. Or when the signal is very negative, we would also assign it a probabilistic interpretation of being close to 0 likelihood that the event would occur. When the signal is close to 0, we would like it to have an interpretation of it being an equal chance between occurring and not occurring. So there are many types of functions that have this property of having this type of sigmoid shape and S-curve that goes between 0 and 1, which maps all of the values on the real number line to this interval. We're just going to choose one out of convenience. So the formula we've chosen for this particular sigmoid function is written up here. And you can check that it actually obeys this interpretation, right? Do a thought experiment where S is very large. In the case where it's very large, both the numerator and the denominator terms that I've underlined will be very large, and the 1 will be negligible. So these two terms are the same, and it will approximately equal to 1. Again, leading us to the interpretation at the bottom. What happens when S is very negative? In this case, these two exponential terms cancel out, and we're left with something like this, which is going to tend towards 0. And let's check the case when we have a 0 as the value for the signal. In this case, the exponential term will be 1, and we'll end up with something like this, which gives us our 0 intercept. Again, this is a soft threshold, and we can contrast that with the other possibility that we can use with the signal, which we used in binary classification, which was the sign. We would be introducing a hard threshold, which inflects exactly at the 0 signal mark. Now we want to make the point that we're interpreting the signal as passed through this sigmoid function as a genuine probability. This is because logistic regression infers a value between the interval of 0 and 1. Let's take a look at what we mean by this through an example. Let's say we're predicting heart attacks, and we have certain types of input, for example, several different health factors. These factors all might have a bearing on whether a heart attack is going to occur for a particular person, say within a particular interval of time, for example, within the next 6 months. As some of the input features might affect the prediction of a heart attack nonlinearly, we may first want to transform these through a nonlinear mapping informed by our prior knowledge. Whether we do so or not doesn't actually matter for our interpretation of logistic regression. Again, we're just taking the weight vector of theta, timesing it by the observation to get out a linear signal. And that linear signal we can think of as some type of score, a risk score associated with the likelihood of a heart attack. We want to emphasize this point that the logistic regression is computing a probability. This is because the inputs to the algorithm of x's and y's consist of y's that are just binary, either +1 for a heart attack that actually happened historically in the data, or -1. We can't measure a probability based on the input itself because it doesn't contain this information, but we're going to infer it and then output that probability. To understand why we say it's a genuine probability, it's because, again, we have a binary y, and we can think of the output as being generated by some type of noisy target function. The actual function that we're trying to learn looks like this. For a particular positive example, we're going to say that the target function that we're trying to mimic is going to be f of x. And for any negative example where there's no heart attack within the 6 months, we're trying to learn the converse. It is a noisy target function. As we can imagine, there are many different patients with different measurements of x, some that might be identical, some of them that will have had heart attacks later on, and some that may not. So we definitely have a noisy target to mimic. The logistic regression algorithm has to make do with the data that we have and infer a probability of a heart attack given this information. So we're trying to learn a set of parameters theta that is going to match this hidden target function as best as possible. In the post-class lecture, we're going to go through how the cost function that we've outlined here comes about. But for now, let's just take it as it is. I'll just briefly touch upon the explanation that we have for the loss. Here again we have the signal. When the signal is a very positive value and the actual output is also positive, then this entire term is going to be a positive number, and the negative exponential will be close to 0, which matches the intuition that when we have a correct positive classification, there shouldn't be any cost. It's going to be similar for the case where we agree that it's a negative classification, because when we take the signal and multiply it against the classification, will still result in some type of positive term, just like we had for the positive case. And so the negative exponential will be the same. It will be close to 0 and there will be no cost. But in the case there's a mismatch, for example, when the result is negative and our signal is positive, or when the signal is negative and we have a positive classification, there's a mismatch. And this particular term will be a negative value. This will lead to the exponent being a positive value and there will be a cost for it. We can compare these against linear regression, whose cost function we've seen before. We'll see in post-lecture that the linear regression has a closed-form normal equation that we can associate with it. But the logistic regression doesn't have a nice closed-form solution, and we're going to use iterative algorithms for solving the problem of finding the optimal set of weights.